Why do you expect them to be different? They will be different mildly. There will be some difference, obviously, due to some, there's always some randomness here. So because of that, you will see that. But do you expect them to be very different?
Would you say that you expect it to be normally distributed?
And sometimes, uh, yeah, so as data distribution at every fold could be different, and maybe
Exactly, that we
some
have
fold
addressed.
could be easier and harder to predict as well.
Exactly. If the data distribution is very different, then they are going to be very different. The validation errors are going to be very different. Nimesh, you have a point to make.
Yeah, Professor, I think they would be different, but they would be very close to each other because they're coming from the same data set. So, irrespective of which subset is being used as a validation set, it will still be it will be different. But I do not expect that to be very far away. But this could give us a very good output from the same set of data, like which validation data set gave a more accurate R-square values, So, and then we can continue to use that for our final evaluation.
That's a very interesting approach. Yes. Okay. Now,
Yeah. Thank you.
Now, I'm going to give you two situations. Okay. So, since the data is clean and the folding is clean, we do not expect the validation errors to be very different from each other. Now, the second question is, do you expect if they are not very different from each other, let's say we are looking at the mean validation error. Do you expect the mean validation error to be high or low? That's the correct answer. We cannot say. The reason is, I have not told you what the model is. The mean validation error, no, if you take the mean of all these 10 validation errors, okay, and if you look at them, and the value of them going to be high or low, there is no way we can say it's just low or it's going to be high, because it depends upon the model. Okay. Remember when we were doing those what shall I call it, fuel efficiency or concrete. Remember that concrete compressive strength, that data I showed you. So in those kinds of data, what if we had, instead of using all the 6 independent variables, we used only 1 or 2 of them when all the 6 are needed? Then we would not be using enough information. Therefore, you expect the errors to be high, right? What if on the other hand, these are all truly independent of each other, and theoretically there is actually no interaction among them. But what if I had used a few interaction terms? Again, you are going to expect the errors to be high, right? So for the validation set, not necessarily for the training set. Therefore, whether the errors are going to be high or low depends actually on the model. So the ideal case, what we want is, we want all the errors to be close to each other. That we can guarantee by doing good pre-processing and doing a good k-folding. But ideally, we want the errors to be close to 0, the mean error to be close to 0. This is what we would need, we would expect, right? But what are the other things we could find? We could find situations where the errors are close to each other, but they are far away from zero. The mean is far away from zero. Or we could have the mean to be close to zero, but the errors are quite varied. And the compromise between these two extremes is this, where the errors are varied, not so bad as in the bottom left, or not so tight as in the top right. And also the mean error is not so high or very close to zero. So this is a good compromise. What happens in real data, I'm going to show to you in the next few slides, is that the ideal case is never achievable. The ideal case is never achievable. We could end up having this either this one or the bottom left or the top right. But actually what we want is, the better model would be the one that's shown in the bottom right. Okay, bottom right. This is what we will be shooting for. One type of models would lead to this. Okay, very low error in the test set, but a very high error in the training. And some other kind of models would do like this. A good compromise would be something like this. A little bit variability and a little bit less mean error. Okay. What are these? These two are okay. So remember, when I say model, what I mean by that is how many variables or what is the number of parameters I am putting in the model. Okay. So I'm going to skip this. You get an idea. So when I say model, remember the number of parameters. Let's say even when you have 5 variables, that is 6 parameters, you do 10-fold validation. Then you realize you don't need all the 5 parameters, or for 5 variables, you go to 4 variables. You again do 10-fold, get the mean and standard deviation, so on and so forth, right? So in essence, if you are trying out different models, let's say you try out M models, you are actually doing 10 M attempts, because for each model you are doing a 10-fold cross validation. Okay. From among these, you will have to choose the best one. Okay. You will have to choose the best one. The best one here is not the one that's going to have just the mean to be close to zero. Because when that happens, the unpredictability in the error might shoot up, and vice versa. And vice versa, right? So we need to find a way to deal with this idea. Okay. And this idea, especially this one I showed in the earlier slide, these two extremes and the compromise, that's called the bias and variance in a model. Okay. So I'm showing you 3 graphs here. The data points, as you can see in all of them, are the same. Let's say it's one variable model. No, what's one variable? So X along the X-axis and Y in the Y-axis. Okay. So that's the first model. What is the first model? I'm drawing a straight line model, linear model. Y is a linear function of X. That's what I'm saying. So I have 2 parameters. Whatever these are, don't worry. What do I find? I find R squared value to be 0.47. The best fitting straight line explains about 47% of the variability in the data. Well and good. Can you do better? Yes, if I can include the squared term, cubed term, 4th quadrilateral term, quadruple term, 5th power, 6th power, so on and so forth. So when we try polynomial fit for this, I got 6th power polynomial. What does it mean? 7 parameters. A 7-parameter model gave me perfect fit. Perfect fit. Why? R squared is 1. Every data point is correctly predicted. Okay. Here is some intermediate one. Let's say this is 1, this is 7, this is 3 parameter model here. Okay, that's what we have here. Prince Dubey, please go ahead.
Sir, the model in between, so the middle one, it actually trying to 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 connect all the dots. It
Correct.
doesn't, but it doesn't look like a real world, model, because it is trying. It looked like a greedy approach where it is going for a perfect fit. But in real world, I haven't seen such situation.
Correct.
So,
and we don't want such situations. We don't want such situations, because what happens is this. This is what this model is for this particular data set. When a new data point comes in, okay, let us say I get a new data point somewhere here. Okay, 1.5 and it's 4.7. Let us say that is the data point I get. Okay, then to fit that data point also, okay, I will have to change the model drastically to get the same performance. To get the same performance, I will have to drastically change the model. Maybe I'll have to go for a 5th degree polynomial. Maybe it will come down like this, or maybe go for a 7th degree polynomial. I do not know. Okay, so we don't want that. So every time a new data point comes in, this model has to be changed to get similar performance. But the same point here, 1.5 and 4.7, when I get it here, okay, this model is not going to change much. Maybe a small change in the slope, a little bit of a change in the coefficient, that is the intercept, for the same performance, but it's not going to drastically change. In fact, it might not change as much. Okay, but the error for that point will be very high. The error for that point in this case also will be very high. If you use this same model, for that point, 1.5 and 4.7, the error will be very high. Here also the error will be very high, because you see this much error is there. But if you go to this third model, okay, the error will be small. Okay, error will be small. So we don't want the one on the left. We don't want the one in the middle. We want something like in the right, which is like a kind of a good compromise between these two. So we call the one on the right hand side as the optimal model. The one on the left hand side, that's too simple a model. It is not using as many parameters as are actually required. So this is called a biased model. The one in the middle, it's too complex a model. Every time the data changes, the model has to change. This is very much data dependent, extremely. Even for small changes in the data, the model will change. This is an extremely complex model. We call this an overfit. Perhaps we have more variables than needed for optimal performance. The one on the right is probably the one that's optimal, gives reasonable fit. Okay, we don't have to meddle with the model, change the model every time a new data point comes in. We don't have to do that. Also, the R squared is very high. Okay, so usable model. The one on the left is called high bias, because we fix it. It's going to be only linear. Okay. The one in the middle is called high variance. The data tells whether it's going to be linear or quadrilateral or sixth power or whatever. Right. The one in the right, it's kind of we fix it, but except that it's slightly better than. It's a good midway between high bias and high variance, so it's optimal model. So this is the kind of thing that we are going to look for. A good compromise between bias and variance. You could see that the one on the left hand side, we are fixing it with a straight line, a linear boundary. Therefore, you do have quite a bit of an error. Okay. The one in the middle, you see the surface, the boundary is a very complicated surface, trying to catch every nuance of the data. So this is a high variance model, whereas the one on the right is the optimal model. This is obviously a classification problem, okay, whereas the earlier one was a regression problem. Right? So what am I trying to arrive at with these two situations? Okay, what am I trying to arrive at this? And by model, we mean best way to explain data or connect data dots. Best way to explain data is what I would mean, not necessarily connect data. So the test error is also low. When is that? And training error low, then it's a good model. That's what you will not get. Johnson test error is also low, training error is also low. Let's see that. That's what we are going to see now. Okay, let's check that. Let's start with the training set. Okay, let us say we have a underfit model. Okay, you have very few parameters than needed. What kind of errors will we get in the training set? We will get obviously very high errors because we don't have enough parameters, right? So what I do, I keep increasing the complexity of the model. By complexity, I mean number of parameters, simplistically. Okay, number of parameters, let us say. So as I increase the complexity of the model, that is, I bring in more and more parameters, I am starting to understand the data. I'm starting to model that data in the training set more and more accurately. Therefore, the error in the training set will keep decreasing until I reach a point where I have reached zero error, as we saw in the previous case, when I have too many parameters, which is the overfitting situation. Therefore, when we are dealing with training set, as we change the model complexity, we will get something like this. The training error will be very high for the underfit, and then as we increase the complexity, the training error will go to zero and can become zero and stay at zero. Right? So that's for the training set. What about the test set? In the test set, we saw in both these examples that whether it is underfit, high bias, or overfit, the error in the test set is going to be very high. When new data comes in, we expect the error to be high in both these cases. But when you have optimal model complexity, that's somewhere in between underfit and overfit, you have the least error. So for the test set, you would expect, or the validation set, you would expect a curve like this. Okay, you would expect a curve like this. So what does it tell you? That you cannot have the cake and eat it too. That's what it tells you. You cannot have training error to be low and also the test error to be low. You cannot have that. You could have this. You could have both the training error and the test error to be high. That you can have. But training error to be low and the test error to be low, you cannot have that. You cannot have that. Okay. So what is the best compromise we can have? We can have training error to be some number, test error to be some number. Both of them are not too low, both of them are not too high. What is high, what is low? I have no guideline. Don't ask me that question. I have no guideline. So how do we know that we are in the optimal region, optimal complexity level. Prince Dubey, please go ahead, ask your question.
I think, sir, you are about to come on the same solution.
Yes.
Basically, what I'm trying to ask is, so it means coming to a optimal model. It's always going to be a hit and trial step, right? Because achieving an optimal model because price variance trade-off.
You draw this curve. You draw this curve.
Mm-hmm.
So you
Region
try
is 0.
all models of different complexities, going from underfit to overfit, and find where your training error is minimum.
Okay.
So in real model building exercise, you draw this curve, and then you identify your optimal model and use that model. So you see it's a validation test. Use that model, go do a final check on the test data, and then go deploy it. Okay, so this is what you have to do actually. Okay, so what is the guideline here? You can, let's say you start with one model and you get a fairly good idea whether it's overfit or underfit. How? If the training error is very low and the test error is quite different, then you know you are in the overfit region. Yes, Suvir Bajaj, please go ahead.
So can you explain the red line again, please? The validation test error increasing.
Red line is,
yeah.
When the model is underfit, that is, you have a very biased model. Let us say you have a linear model when you actually need a quadratic or cubic model. That is, you have only 2 parameters when you need 4 parameters in reality. Okay, that is underfit. In the underfit case, you will have errors in the training set, errors in the test set, both to be very high.
Yes.
Whereas when you come to the overfit region, the errors in the training set is going to be low. It can be even 0.
Yeah.
But in the test set, it's going to be high. Unless the extreme situation where your data point falls exactly on the curve that you got.
So is this red line an exaggeration? I mean, relatively high, but is it an exaggeration?
Yeah, it gives an idea. Gives you an idea how things go.
Got it. Thank you.
Yes. Sam Liang, please go ahead.
So I think we can look at a gradient. When the gradient is 0, that will be your optimal point.
Exactly. That's correct. That's what you do. Okay. So you choose this optimal point, looking at the gradient as he correctly said. No, choose that. That's your best model. So what do we have? When we have underfit model, both the training error and the test error, they are very close to each other, and both are high in value. When you have such situation, you have this underfit model. When you have overfit model, okay, you had your training error is very low, but the test error is very high. I tell you one problem I worked last year. This was a forecasting problem. I was working for a $1 billion spare parts manufacturing company. They wanted to have product level, the individual item level forecast. They gave us 3 years data, very, very intermittent data, in the sense that data is very sparse. Okay, they wanted us to give demand forecast for each item. They had like about 2,500 items. And in my initial exuberance and enthusiasm, what did I do? I went ahead and created variables after variables after variables after variables, right? So that's called feature engineering. Created a lot of features, came up to about 104 features, for a model. And my absolute in the magnitude of the relative error, okay, relative to the baseline. What is the error I have is called MAPE, mean absolute percentage error. Okay, that was like 3%, 4%. That was awesome. Awesome error. No, 3-4%. But then when I tested it on the validation set, I had 100% error. Right? 100% error. So this is very common. Many a time, even when you know things very clearly, we could very easily end up in the overfit region. Okay. When you are learning about deep learning, which is in the next course, this is a very big problem. You will very easily fall into the trap of overfitting. Okay. And then once you fit the model, you are very happy, but go and apply it on the test data, you are getting extremely erratic predictions, and you know that you are in the overfit region. Right? You are in the overfit region. Okay? So this is very easy. Falling into the overfit trap is very easy. So be careful. Test for it. Okay. So what do we actually do? We plot this. This is one of the most important graphs in the entire machine learning world. This graph you draw, training error, test error, and choose where the gradient is 0 for the test error, and that is what you would use as the best model. Sometimes instead of error, we would use accuracy. If you use accuracy, what happens? It will be inverted, right? The errors will be for underfit, the accuracy will be very low. Okay, and then for the training set, as the model complexity becomes more and more, accuracy becomes very high, reaching 100% for overfit. For the test set, test accuracy will be very low for underfit, keeps on increasing, and then again starts decreasing as we go towards overfit. Okay, so it's a inverted image. Okay, so that's what you would find. So this is very important. So, okay, so the test error is also low. Training error. Okay. If you use simple linear regression, we end up with the underfitting. In some cases, if you use simple linear regression, you could end up with underfitting. Okay, in some situations, yes. Now you see, to get to this best point, people ask the question that can we identify this optimal model, in one shot? Of course, you cannot do it in one shot. Okay? But what is the easiest way of dealing with this? What is the easiest way of dealing with? You see, you are not only looking at performance, you are looking at performance, which I mean the error, also the complexity. Okay, also the complexity. So how do we deal with this? Now, both of them together. That's what you want, right? You want to deal with complexity as well as performance together. And this is where the idea of regularization comes in. Okay. Here, I'm going to show some crazy looking equations, and I'm going to tell you something. Take them as definitions and just memorize them. I'm not going to go ahead and tell you why these are these way. Okay. But anyway, so for the next 10-15 minutes, some important information that you should have in the back of your mind. So what do? Think about this. We want to decrease the error, and also we want to not have too many parameters. Okay. So what do? We start with the most complex model we can think of. We start with the most complex model we can think of. But think about this, when you have the most complex model, complexity is very high, but error is practically 0. Okay. Now, what we do is we do some trick. And put performance and complexity together in one big function, and then minimize that function. That function is called the regularization function, or we can generally call the cost function. What is this? As you can see, minimization with respect to beta, that is a parameters. Okay, so it might be a frightening math expression, but it's very easy. There is a plus sign. That means there are two terms here. There is one term with this this sigma summation. There's another term with this second sigma. Okay, what is the first one? First one, if you see, for all data points, n is the number of data points. For all the data points, we are looking at sum of squared differences, sum of squared errors, sum of squared errors. Okay, so because this is the model, right? This is the model. When I is equal to 0, xi is 1, beta naught plus beta 1 x1 plus beta 2 x2, beta 3 x3, so on and so forth, up to m. When you have x, there are mx, right? This equation has to be slightly modified, but I do not know whether I can do that. Let me see. Yeah, I can do that. So I'm going to scare you a little bit more here. Yi minus beta yj minus beta xij. Yeah. Okay. So this is, so what do we have? We have one term for the error, and if you look at the second term here, it is only the parameter values, beta, right? So over all parameters, okay, we usually don't care about the intercept. We are only worried about the coefficients. Therefore, we start from I is equal to 1 to m. Okay, so beta parameters. And why do we set it squared? Because some of these parameters can be positive, some of these parameters can be negative. So if you don't square them, maybe this optimization process will tend to cancel out each other. So instead of taking us to the optimal minimum, optimal solution, it could take us astray somewhere. So we need to square it. To keep all these positive, we need to square this, right? So you have two terms, the performance term, the error term, and the term that's consisting of parameters only. Parameters, number of parameters. That means the second term is the complexity term. The second term is the complexity term. Okay. Now, what is this lambda? I said lambda 2. I'll come to that y in a while. Let's call this lambda. Lambda is called the hyperparameter or regularization parameter. It is not fixed by the minimization routine. We have to give value to it. We have to give value to it. Okay. So what did I say? I said we start with the fully complex model we can think of, right? So when I set lambda to be 0, this term goes to 0, and we have all the lambda, all the parameters here. That means we are looking at the performance of the most overfit model. So, but when lambda becomes very large, let us say, okay, let's say when lambda becomes very large, if I have to minimize this entire thing, okay, then I will have to minimize this second term, complexity term. So what would that mean? I would push many of these parameter values to be close to 0. What does it mean? I am moving towards an underfit model. So by systematically changing lambda in this expression, I go from an overfit model to an underfit model. That is all we have to do. Okay. So what do? We start with a lambda value. We start with the lambda value close to 0. find the cost function, okay, and then keep calculating the validation error every time and change the lambda value, calculate the validation error for this cost function after fitting the model, okay, after adding the best model, find the validation, so on and so forth. Keep doing it, keep increasing the value of lambda, and somewhere there you will find the minimum for this. Yes, John Sirani, please go ahead.
Okay,
If you are
sir, you mentioned about lambda is 0 in the sense it is underfitting, is it? If you put, yes.
It is what, if lambda is 0,
that means error.
The second term is gone.
Yes, sir.
But that doesn't mean the beta terms
errors
are 0.
Okay.
All the beta values are still there.
Okay.
You are using all the beta values. That means
I understood. Got it, sir. Got it. Thank you.
So when lambda is very high, the only way you can minimize this entire expression is sending many of these beta values to be close to 0. That means when lambda is very high, you are going to the underfit regime. Okay, that's the basic idea. That's all. So vary lambda from 0 to a very large value, plot the validation error, and see where the minimum is. That's all. Okay, use the corresponding values of beta. Okay, that's your model. This particular expression is called ridge regularization. Don't ask me why it's called ridge. I'm not going to tell you. That's the reason for it. Take it up as a bedtime reading sometime. No? So it's a ridge regularization. It is also called L2 norm optimization. Why L2? 2 stands for the power here. And we are squaring it. So it's L2. What is L? L stands for the French mathematician Lebesgue. I think that's how he is pronounced. I might be killing his name. It's spelled Lebesgue. So some people not deliberately pronounce his name as Lebesgue. Okay, but I think his name is pronounced Lebesgue. I might be wrong. If anybody speaking French is here, they may tell me how his name is pronounced. Great mathematician. He developed the theory of integrations in calculus. So that's why it's called L2. 2 stands for the power. If it's L2, is there L1? Obviously, if you set the power to be 1, but we don't want to set the power to be 1 directly, because if you set the power to be 1, all the beta values, some positive, some negative, they will get cancelled. Therefore, we are going to use the absolute value of beta. These two expressions are very similar except for this regularization term here. Okay. And this is called L1 norm. It's also called lasso regularization. You see, ridge is a name, lasso is an acronym. Lasso stands for some kind of what is called shrinkage. I'm not going to explain again what it is. I'm going to tell you the difference between these two. So this is the definition. The idea is by changing the lambda, you can go from overfit to an underfit model, and therefore you can identify somewhere in between the two extremes is where your optimal model is. Okay, in one shot. That's what it is. So here is an example from a toy store. Okay, so this actually, we used to call it a toy example. It's a toy store example. Okay, somebody had asked for a. Okay, it's not coming up. Let me check what the chat messages. Okay, it's not coming up. I'm not going to spend time on it. Okay, so what is it? This is a toy data where the store collected data about its customer. Many things like what is the family size, what is the number of children, the age of the oldest child, the age of the youngest child, okay, and how often they have visited the store in the previous 12 months, what was the last time purchase, all these different things, okay. So 13 parameters they had in the model, linear regression model. What is it? They want to predict how much this customer would spend in the coming year. Okay, that's all. So this is what the k-fold cross validation did. What we have done, we have used ridge regularization. Okay, so, sorry, this is lasso regularization. Okay, lasso regularization. What we have done is started with lambda value of very small 0.001. Look at this, log lambda is -3. That means lambda value is 0.001 and went up to 10,000. Okay. Log lambda is 4. That means 10 power 4, about 10,000. So that's a huge range over which lambda is varied. Okay. And as you can see, what is this? You see the red dots? These red dots are the mean of the validation error when we did k-fold cross validation. For every lambda value, we did k-fold. Okay, for every lambda, we did k-fold. So we got the mean validation error as well as the standard deviation of the validation error. Okay. Now we plotted this. In this, we find where is the lowest error. The lowest error happens to be the one corresponding to the log lambda value of -2. This dotted line on the left side. Okay. This is where the lowest mean validation error is. Okay. And if you, the other dotted line, the one on the right, okay, that tells you the log lambda value where the mean validation error is still within the one standard deviation for this one. Okay. For the lowest error. For the lowest error, that's the standard deviation. This is the highest error which is still within that one standard deviation. Therefore, technically, these two are equivalent. Not technically, statistically, these two are equivalent. Okay. Now, which one should I use? Should I use the lambda value of -2 or should I use the lambda value of 0.1? Okay. To understand that, we go and look at the top. The top, this is where we have listed the number of parameters that are non-zero. As you can see, as the lambda value increases, the number of parameters that are non-zero, they keep decreasing. That is, we are going from overfit to underfit. Okay. So what do we want? We want a good compromise between these two. So we want that model which has the least number of parameters, but also does the best performance. The best performance is here, but the same performance is achieved by a model with about 8 parameters. Okay, so this is the model we will choose. So what am I saying? Sometimes you won't have a smooth, very sharp peak. You might have a plateau. So in the plateau, you have to choose the one with the smaller number of parameters. Okay, so this is what we actually do in any real time, or what we call within quotes real life model fitting, right? So let's go through the differences between ridge and the lasso. Ridge regularization reduces the coefficients. They push the coefficients value as you increase the lambda value, the beta values get closer and closer to 0, but they never become zero. So technically, ridge does not get rid of overfit. But in certain situations, what you can do is, you can say, if my parameters are below some number, I'm going to set them equal to 0. You can do that. Okay. I like you to think about when you can do that, and maybe we can discuss this after the break. Lasso, on the other hand, will make certain coefficients go to 0. It will set certain coefficients go to 0. So if you want to definitely reduce the dimensionality of the problem, that is, if you want to make certain coefficients to go to 0, you should use lasso. On the other hand, ridge is very robust. Okay, ridge is very robust and unique. Lasso, we cannot say that it's good for dimensionality reduction. Ridge is very stable even when the data size is small. What does it mean? You have 30 parameters, you have 30 variables in your model, but you have data from only 25 subjects. So the data size is smaller than your number of your feature space. Where can such thing could happen? It can happen in many fields. For example, when a newly started clinic, okay, a clinic can have patients' data. Okay, they might have 100 different parameters collected about the patients, but in the first week they had seen only 20 or 30 patients. Okay, that's the situation, for example. Okay. Lasso, on the other hand, will not work well in this situation. It needs a large data set. Okay. And finally, ridge is very stable when you have multicollinearity. In fact, it gets rid of multicollinearity. Ridge gets rid of multicollinearity. Lasso does not. Okay. Lasso does not guarantee removal of multicollinearity. So when you are worried about multicollinearity, when you think the data set is small, or when you have a situation where the data size is smaller than the feature size or the dimensionality, then you should use only ridge. But if these two are not a problem, you are not worried about multicollinearity, and you have enough data, then go ahead and use lasso. Okay? Because in that situation, lasso is guaranteed to give you the optimal model. Okay. Now, there are few situations how can you know to keep all parameters keep or make few parameters 0? That's something I wanted you to think about, right? So we can discuss about this. Okay, let me give you the answer. Okay. You can do that specifically in certain situations where every variable in the model has been standardized. Okay. By that, what do they mean? You remember the Z-score we talked about. So you had transformed every variable in the model to its Z-score. That means now all variables are on the same pedestal. Now, therefore, if you look at the coefficient values, when the coefficients are small, you know that that variable has the least effect. The one which has a large coefficient has a large effect. Now you can set a threshold. If my coefficients are less than 5% of the total, okay, you add all the coefficient values, absolute values of the coefficients, okay, and each coefficient you divide by the total value. Now you can come up with a rule saying if it is less than 0.05, then I will throw off that coefficient. I'll make the coefficient be equal to 0. That way, you are forcing, you are essentially what you are doing, you are throwing away least influential variables. Okay, so that's some kind of a threshold like that could be done. Okay, in ridge. Lasso, you don't have to do this. Yes, Prince Dubey, please go ahead, ask your question.
So, sir, as you already mentioned it into previous classes, when we have a similar kind of data in a particular column, which is almost stagnated, right? So in that case, removing that as well as the correlation between the two features, which are very much high, then also one of them needs to be get out, right? Because yeah. Okay.
Yes.
So these
And
two approaches generally, these two approaches are, you know, are very common, which I generally prefer to use. But is there any other thing as well we should try to focus to remove the parameters which we believe will get a very good model?
I saw some of your part of your question came out kind of jagged for me. Can you repeat the question?
Okay. So correlation and correlation is one where we can find, okay, which one is needs to be get removed, and the other one is stagnated value within across different records in a particular column that should also be removed. But other than these two, what other measures we should focus to decide, okay, these are the set of parameters which by which I will be going to train my model?
Okay, see, you look at the correlation, you look at the VIF, and you look at you know okay, some of the, okay, let's think about this question. If one variable is highly correlated with some other variable, one of these two variables can be dropped because they essentially carry the same meaning.
Yes. Yeah.
That's one thing. Second thing is, if a variable is fairly constant across the data, that is, the variability of the variable is small, then also it means that variable has no information.
Yes.
Okay, so you can drop that variable also. The other thing is we do not know. In real data, I would think in enterprise data, okay, it would be a pain to go ahead and study. I mean, finding out variables that are not varying too much is easy, but studying all the intercorrelations is going to be very difficult. Okay, so in that situations, I would blindly go and start using ridge. Okay, I'm not going to assume whether the variables are related or not. Let there be relationship. I don't care. Ridge will take care of it. If the variables are related, ridge will take care of it. Okay, it will decorrelate those variables. Ridge will do that. Okay, lasso will not. So if I expect multicollinear to be absent, then I can go ahead and use lasso. Or if I don't worry about multicollinearity, go ahead and use lasso. But think about real data. When you have lots of variables and lots of data, we really cannot say which way we should go. Whether we should go ridge or lasso, it's very confusing. There is no guideline. So what do? We do both. Okay, we do both. We put them together in one big regularization. Okay, we do lasso L1. We also do ridge. Combine them together in one big cost function. This is called elastic net. Okay, so elastic net regularization is probably the one you will use when you are completely unsure which way to go. Then use elastic net. What does it do? Combines both lasso and ridge using a proportionality parameter. No, it's a number alpha. It's a number between 0 and 1. So when alpha is 0, we are doing ridge. When alpha is 1, we are doing only lasso. By varying the value of alpha between 0 and 1, we are bringing in different weights for these two regularizations. What does it mean? I'm somewhat confident that there is no multicollinearity. Maybe I will use a value of alpha to be 0.7 or 0.8. Why? Because I'm not too worried about ridge. And I'm not worried about removing multicollinearity. Okay, so I give high weightage for lasso because that will reduce the dimensionality of the problem, and I'm happy. My systems can work with the smaller dimensionality. On the other hand, no, I need to be sure that multicollinearity is not there. But I would also like to reduce the dimensionality as much as possible. Then I give lots more weightage for ridge. That means set alpha to be 0.2 or 0.3. Therefore, I get a larger weightage to ridge, smaller weightage to lasso, and then find the overall performance. In objective sciences, in objective fields, objectively what we should do is treat this as another hyperparameter, change the value of alpha, okay, from 0 to 1. So plot the best, plot the cost function that you get over alpha, okay, and see for what value of alpha you get the minimum, and use that. That would be the optimal model. Okay, so ridge and lasso regularization together in an elastic net is what you would do in most situations when you are not clear about how to go about it. Okay, in fact, many software they would have this parameter is when you do regularization, you would have this parameter. I call it alpha here. Some software call lambda, confusing with my notation. Some software call them beta. So understand what actually it means. It means the push and pull between the two types of regularization. They always have the alpha value set to be 1. So lasso is taken as the default option in many software, but you can play with this alpha and then have a good compromise between lasso and ridge. And this is how we actually fit models in the enterprise level. Okay, so what did we do in the past hour or so? We understood that having an underfit or an overfit model is disastrous. So we need to find a compromise between the underfit and overfit. The compromise between the underfit and overfit model is obtained using regularization techniques, and therefore we use the ridge regularization when we are very sure that we want to get rid of multicollinearity, and or if the data set is much smaller than the feature space itself. On the other hand, if the data size is large, and if the main aim is to come to the optimal model, that is get rid of the extraneous parameters, then go for lasso regularization. And when unsure, combine both of them in elastic net and use that to come to the optimal model. So this is the approach we will take throughout. Okay, so this is I have demonstrated this for linear regression, but of course we can use it for every other model that we will be building in the future, including neural nets and deep learning networks that you are going to build in the next semester. Okay, we can use them. Idea is this: regularization consists of one term that talks about the performance and one term that talks about the complexity of the model. Okay, put together, we get a cost function and minimize that cost function. Okay, if you understand this, regularization is an easy thing to do. Okay, so with this, I'll stop here. And what we will do is we'll take a 10 minutes break. And when we come back, we will start on unsupervised learning. Okay, we will start on unsupervised learning. Let me think. No, we'll do another thing. We will still continue with supervised learning. We will talk about something called decision trees. Okay, decision trees. We'll talk about something called decision trees. We'll take a few minutes break and come back. Okay, decision trees is what we will talk about. Okay. So what we are going to do now is look at a new type of classifier called decision trees. Even though decision trees is predominantly used and introduced as a classifier, it can also be used as a regressor. Okay, it can also be used as a regressor. Now, the one classifier technique we learned earlier was logistic regression. Right, the model that gave us a linear boundary between two classes. Decision trees is a non-linear classifier. So we are not going to have a single straight line or a single plane that separates regions belonging to different classes. Okay. In fact, this can be used to do multi-class also, but we'll still use binary classification to demonstrate. Okay. So we will right away jump into an example problem. The problem I want to talk about is this particular problem where we have some people data, people, their age and their annual income in thousands of dollars. Okay. And everybody has been labeled as whether they are labeled as green or red. Green are those who have taken loans, maybe a housing loan. Red are those ones who have not taken that particular loan. Okay. So green and red, two classes. Now, if you see this data, it should be obvious. It should be obvious that logistic regression will not work in this case because the two classes are intermingled fairly well. Okay. Maybe you should try to come up with a straight line like this, somewhere here, where the greens are low, but the reds on this side are high. So any kind of a linear classification scheme you try in this, we would fail very miserably. Okay. Now, added to that, okay, if I ask you a question that a person aged 39 and earning somewhere about $85,000 per annum, would you say whether this person is a loan taker or not? Okay, whether it's a loan taker or not. Okay, so this person is here. So we do not know how do we go about looking at this. Or another person, same age, but a different salary. Or you could say, same salary, but different age. For example, how do we categorize these people? Okay. And that's the kind of problem we are going to solve today, right now. So the same data set. How do we go about solve this? Yes, I'm going to do some kind of a orthogonal dissection. What is orthogonal? Orthogonal means perpendicular to some axis. Orthogonal means perpendicular. Okay. So I have a dissection here perpendicular to the age axis. Okay. I dissect here. And then what I would say is, I would say perhaps on the right hand side of this line is the non-takers, and on the left hand side is the loan takers. This is like having a logistic regression, but instead of having any general slope, it only has this perpendicular to this one axis. But of course, you see, this is a very poor categorization. It's a very poor classification. So what do we do then? I then go ahead and then do another split. Okay. So what I do is I do another split. Where do I do the other split? Perhaps for age less than 41. Age less than 41, I can do another split. Age equal to or greater than 41, maybe I don't have to. But for age less than 41, maybe I can do a split like this. That is, for all people with age less than 41, I ask the question whether their annual income is less than or equal to 101,000 or whatever that number is, 112,000. This line does not correspond to this, but anyway, let's say that's the question I'm asking. Okay, maybe I can move this a little higher, right? Right, I ask the question whether the age is less than, sorry, the income, annual income is less than 112,000. If I say no, it's greater than or equal to 112,000, I am pretty confident that this region, these are the people who have not taken loans. Sorry, who have taken loans. So anybody who falls in this region, I am going to categorize them as loan takers. How about in this region when they say, yes, income is less than 112,000? Okay, I see it's still a little bit ambiguous. I cannot say for sure whether they are loan takers or not takers. So what I can do, I can again go ahead and do a split here for age, for example. Okay, I can do a split for age like this, and ask the question whether the age is less than 36. If yes, the answer is yes, then I see they are predominantly red, that is, they are non-takers. So anyone in this region, I'm going to call them as loan non-takers. Of course, I have some errors, but that's okay. We know always in any model, we are going to have some errors, right? In this region, I'm going to say this is predominantly green, therefore loan takers. So anyone in this region, I'm going to say these are loan takers, right? So I can continue this. I can continue this, right? I can continue this. For example, perhaps I can draw a line here for this side. Okay, age less than 41. When I say no, I can ask the question: is salary greater than 160,000? If it is yes, then I will say loan takers. If it is no, I'll say no, loan non-takers. Even there, I might want to do some splitting. No, I can keep on doing this. How long can I keep on doing this? I can keep dividing this entire feature space by doing this orthogonal dissections. First orthogonal dissection of the entire space, then each subspace I do orthogonal dissections, and I can continue until every region contains only one data point, right? I can continue this. Who is going to stop me? Maybe it's the number of data points and time I have might stop me, but otherwise theoretically I can do that, right?
So don't you think in that case it is going to be an overfit? Because
Exactly. It's very easy to overfit in decision trees. Okay, you can easily, it's tempting, you know. I can see when I look at this, I can immediately draw a line here and I get this. And then what I can do, I can draw another line here. So between these two, I'll always have this. Then I can draw a line here and then draw a line here. So it is very, and I can draw a line here, okay, and another line here and split this region. It is very easy to overfit in decision trees. Yes, you are very correct. So we have to ask the question, where do we stop? Okay, where do we stop? You get that? This is all we are going to do. The idea is do this orthogonal dissections. That's all. There is no more thing to do. But of course, life is not that easy, right? There are multiple questions we will ask. Okay. First question, you correctly identified that we will end up with overfit. Therefore, where do we stop? That's a very important question. Let's come to the beginning. I said, I want to start with this question, namely, is age less than 41? Why that? Why not start with age less than 45? Or age less than 43? What is so special about this? Okay, so you need to ask a question. Where do I make that split? On the age axis, I am making a split here. Where do I make the split? Once I made the split, then I'm asking the question, where do I make the split here? Why 112? Why not 110 or 100 or 119? Right? Where do I make the split? That's the second question. Both are very important. So these two questions, if we can answer well, then decision trees are over. We have got a very robust classification scheme with us. Because why? It is non-parametric. There is no parameter to fit here. Right? There's no parameter to fit. So if you think of these split points as parameters, then okay. Okay, but you are not going to minimize something with respect to split parameter. Of course, we are going to do that, but let's see what we are going to do. Okay. No, but it's almost non-parametric. Right? So let's start answering these questions. Now, the original two people I chose with this kind of a scheme, both of them will be categorized as loan takers because both of them are in a predominantly green subregions. But on the other hand, if I had had a very different scheme like this shown on the bottom right, okay, if I had a decision tree scheme like this, you see one of them is green, that is loan taker. The other one is a loan non-taker, which is actually correct. Which is correct. So they cannot be both. One person can be only in one of these two categories. So which of these decision trees is correct? Right? Or how can you identify the correct decision tree? That should be the question we'll be asking. So let's, before we move on to that, let's get introduced to some terminologies. Okay. So as you can see, this grows like a tree of decisions. This grows like a tree of decisions. That's why it's called decision trees. Every time we are making a decision, a tree of decisions. We start with this first question. So this is called the root node. This is called the root node. It starts with the first question. The first question you ask, that's what we call the root node. Then we have these decision branches. Okay, we have decision branches. Okay. Every other question you are asking, that's called a branch node or simply a node. Each one of these is a node. The first one is a special one, that's called the root node. Okay. And then from every node we have branches. We have branches. Okay. A branch may lead to a new node, or it may end on a leaf node. It may end on a leaf. Okay, it may end on a leaf. So we have root node, branch node, branches, and leaves. These are some terms we'll have to be familiar with. Whoever decided to call it a tree, they want to have the same mental model, so call them these names initially. Okay. So now here is another more complex decision tree. So it's that these different diagrams are demonstration of showing how it is very easy to go into the overfit region in a decision tree algorithm. Okay. So let's start attacking those two questions we asked. What are the two questions? First is, how do I decide which variable? Okay. Let's say, remember, I first started with age 41. Why start with age 41? Why not start with income 112? Okay. So how do I decide which variable and which split point to use? Okay, at every stage. Once I ask this question, next I ask this question. Why this? Why not a question on age itself again? Right? So at every time, at every node, how do I decide what the node is? That is, what variable, what feature we are going to use, and what is the split point? Okay, that's what we need to understand. This is now complicated by one other nature of the schemes, namely the features, the variables can be of two types, right? Categorical or numerical. Can we treat categorical and numerical the same? Maybe, maybe not. We have to find out, right? So here is an example. This is a contrived example. Actually, what happened was I want to have a binary data, binary class, okay, and randomly came up with these numbers, just random generation. Class assignment was also random, okay, but it so happened something funny here. So this let's assume this was the 2024 US elections, okay. So we wanted to know whether these 10 people voted for Democrats or not. So Democratic candidate at the time, I think, was Kamala Harris, right? So doesn't matter, whatever, two binary variables. Okay. So I consider these three independent variables: homeowner, marital status, and annual income, to model whether somebody is going to vote Democrat or not. Okay. So let's go ahead and start doing decision tree on this. No, technically, no, since it's binary, we can do logistic regression, of course, okay, and see whether it works. But let's use this to decide decision trees. Okay, it's a very poor animation, so it should have come down. So this is what we are interested in. This is our Y variable. Okay, they voted Democrat. If you count, 7 people voted no and 3 people voted yes. So that is the base truth we have, right? Okay. Now, I've not shown you why I chose that. I'm randomly choosing homeowner as a starting point, as my root node. And I ask the question whether is somebody a homeowner. There are 2 possible answers. Yes. Oh, very poor animation, very poor this thing. I do not know. Okay. Let me move this a little down. This also comes down a little bit. Okay. Move this also down a bit. Okay. And you see, yes, there are 3 people who voted yes. Of course, there are 3 people who are homeowners. There are 3 people who are homeowners. How did they vote? All the 3 voted no. Right? All the 3 voted no. And out of the remainder, there are 7 who are not homeowners. And of those, of course, I hate this. So of this remaining 7, okay, obviously 4 voted no, and the remaining 3 voted yes. Again, this problem. Married, no. Okay. So there are 4 who voted no, 3 voted yes. If you look in the left-hand side here, that is homeowners, all of them voted no. So there is no need for splitting this particular group once again. So this actually is a leaf node for us. Right? This is a leaf node for us. But the other one, yes, of course, it needs correction. Now we have to ask some other question because it's not clear. Okay, almost equal split between yes and no. Okay, so I decided to, it's again random. I decided to look at marital status. Okay, so I asked the question married. But if you look at marital status, there are 3 categories: single, married, and divorced. So I arbitrarily split them into 2 categories. One category is married, the other category is divorced and single. Okay. Again, I'm very, very unhappy with this setup.
You can move the table up
But I think,
you can move
the
table a little bit.
yeah, but I think you are getting the gist of what I'm trying to do here, right? So I'm going to just I'll correct this in the handout. When I even share it today, I'll correct it and share it with you. Okay. So when you look at married, no, all the married who are not homeowners, no, married, no, no, married, no, and then no married, no. All the 3 married people who are not homeowners, they voted no for Democrats. Whereas single or divorced, look at that, 3 of them voted for Democrats and 1 against. Now you can look at, now this becomes a leaf node because there's no point of branching here, right? And then this one you can ask, again arbitrary, I chose this, okay, yes and no, and then you see we have this. Okay. So what we have is, we have pure leaf nodes here, 1. So we have, these are leaf nodes, 1, 2, 3, 4 leaf nodes, 2 branch nodes, and 1 root node. Okay. Once you have reached the leaf node, that means you stop there. You don't have to split anymore, right? So now it's very clear. Now you can go and ask, is a person homeowner? Yes, then they did not vote for a Democrat. If the answer is no, then you ask a question, are they married? If the answer is yes, then they did not vote. Otherwise, you ask the question whether the annual income is less than 80,000. If the answer is yes, then they did not vote for Democrat. Otherwise, they voted for Democrats. Okay, so this is the way the decision tree works, a tree of decisions. Yes, Subir Bajaj, please go ahead.
So you started the decision tree with home ownership and ended it with annual income. Is that in the same order in which the columns are placed?
No, no, that's what I'm saying. This is arbitrary. I'm just demonstrating the calculations. How to generate the, what is a root node, what is a branch node, what is a leaf node, just to generate, just to demonstrate that I have given this example. This is not how we actually will do.
Okay, you will come to that later, right?
I'm coming to that in probably the next slide.
Got it, thank you.
or maybe not. One slide more. Okay. So with the, what is the use of decision trees? When you have created the trees of decision, then you can create these rules, right? A homeowner did not vote for Democrats. A married person not owning a home did not vote for Democrats, so on and so forth. You can come up with these rules, right? Now, these are the two questions that we have to answer. How to decide which variable will be the root node, how big the tree should be, that is when to stop growing. Okay, the key for stop growth stopping, or not stop going, it should be stop growing. The key to stop is the purity of the nodes, right? For example, in the previous case, these are all pure. Everything is pure. So we stopped. There's no more splitting there. If we wanted, we could have even stopped here. Oh, sorry, one before that. We could have even stopped here, because married status, if you say if they are single or divorced, predominantly they are supporters of the Democratic candidate, right? They voted for Democrats, so predominantly. So we can stop here, but we just went ahead and showed that you can still split further. Okay, so in this particular situation, you have one very pure leaf node, another very pure leaf node, third one a pure leaf node but not so pure as the other two, right? So how do we calculate the purity of a node? How do we calculate the purity of a node? So here is another example. Okay, I have split this into these three regions. So how do we calculate the purity? Is T1 pure? Yes, everything is green there. Therefore, I'd be tempted to say the purity is 100%. How about T2?
Yeah, that is also pure.
That's also pure, 100%. 100% right. Doesn't matter, it's 100% pure. How about T3? It's not pure 100%. It's not impure 100%. There's no impurity 100%. But anyway, but it's 66% green, right? So it's 66% pure, 2/3 pure, right? Because out of the three, two are of the same color. So that gives you an idea. So essentially what we are going to do is, we are going to look at the proportion of data points in a particular region that belong to one sub-region to calculate the purity, right? So no impurity, slightly impure. Okay, so how is impurity calculated? 1 minus purity is impurity, that's all, right? So impurity, if I put something here, now a new data point comes in, okay, or whatever, when I classify everything in this third region to be green, I get an error rate of 1/3. Okay, out of three, one of them I have misclassified. So classification error in the third region is 1/3. In the first region, it's 0. In the second region, also it is 0. So classification error could be a method by which we can calculate the node impurity. Node is a region where we make the split, right? Node impurity. So how do we define classification error? We define classification error as 1 minus maximum of the probability for each class. J is the class. I put I here. which is wrong. Okay. So P of t, probability that in the tree, in that particular node, okay, in that particular node, something will be in the class J. Class J, that is, it can be class green or class red. Something will be in the class J. What is the probability? In the first thing, probability for green is 1. Probability for red is 0. So what is the maximum between red and green? 1. Therefore, classification error is 1 minus maximum, which is 1, 1 minus 1, 0. In this case, classification error is 0. Right? Likewise, in this case, classification error is 0. Here, it is, let's classification probability that something in this region is red is 1/3. Probability something is green in this region is 2/3. So maximum of these two is 2/3. 1 minus 2/3 is 1/3. So that is the probability of, that is the classification error. It's a classification error. It's a measure of the node impurity. Okay. Somebody has a question or comment? Yeah. What is class J again? So class J, it can be yes. That is, class J is J is equal to 1. J stands for the class name. Class J. J can be yes, J can be no. So what is the probability that somebody voted yes for Democrat? That's some. What is the probability that somebody voted no for Democrat? So there are two classes in this case. Okay. Life is not so simple. Therefore, what happens? People define a slightly better quantity to study the impurity, and that quantity is called entropy. And some of you might be very familiar with it. Entropy essentially talks about the randomness in the data, right? So, and if you are coming from electrical engineering or communications systems engineering, you would have heard that the entropy, which is essentially the measurement of the information in any packet, is given by this quantity called P log P, log 2, by P log P. Okay? And since the probability is always a number that's between 0 and 1, logarithm is a negative number. So we take the negative of this. So negative of P log P. So this is a positive number. It's a positive number, right? So we do that for every class. In this case, N is a total number of class, I is for every class. For in this case, for example, probability that for the region 1, we have the blue, okay, sorry, the green, okay, and then probability that this is for a particular tree, right? For this particular node, probability that something is red. Okay, that's the thing. If you have 3 classes, see again, remember the example is with 2 classes here. It can be 3 classes, red, green, and blue, doesn't matter. Use all the 3, whichever has the maximum, you take that value, and 1 minus that value gives the impurity. Why? Because if, let's say, in one region, in this region, let us say blue is maximum. Okay, there are 10 points here, 3 are green, 2 are red, 5 are blue. If that is the case, we are going to assign everything in this region to be blue. Therefore, 5 of them we are going to misclassify, right? Therefore, 1 minus max is 5 out of 10. Okay, 0.5. So 1 minus 0.5 is 0.5. That's a classification error. Half of the points in this region we will misclassify. Right? Let us say in this case we have 4 red, 1 green and 1 blue. Let us say. Then maximum will be 4 by 6. Right? 4 by 6, 2/3. 1 minus 2/3 is 1/3. So there's a probability that we will make an error in the second region is 1/3. Correct? That's what it is. So similarly, you could also calculate the entropy for each region. So 3 out of 10 is the probability. Use that for the green, plus 2 out of 10 for the red. Use that here, plus 5 out of 10 for the blue. Use that here. When you add all of them and then multiply everything by minus, then you get a positive number. That's the entropy. That gives a total randomness in the node. That's another quantity that people came up with. Okay, this is called the Gini index. Gini index. Some people call Gini. I think it should be correctly called as Gini index. I might be wrong. Okay. I call it Gini index. Now, this is a slightly different from the entropy. Okay. What it does is, okay, entropy is a very nonlinear function of the probability. Gini index is a slightly less nonlinear function of the probability. It's only square, but the logarithm is actually, if you know, it is an infinite series. Okay, whatever that means. So people also use Gini index, and in practice, what people usually do is, very rarely people talk about classification error unless that's what they want to do. So people by default go to entropy, and if entropy is not easy to calculate or not, they are not satisfied with what they find, people also try out Gini index. That's how people use these three different metrics for understanding the node impurity. Okay, so yes, John Sirani, please go ahead.
Rajesh sir, is it we have to select between these 3 impurity models, or somewhat system can tell us, okay, now I'm confused with my data, a lot of uncertainties are there, then go for entropy, or
No, it's you do. It's you do.
Okay.
You make a decision. Yeah. Okay. So in most cases, entropy will be good enough. Okay, and we'll see why in a couple of slides from now. I'll show you why entropy is good.
Got it. Yeah. Thank you.
So whatever I was mentioning here is the exact calculations. Okay, for classification error. Let's do another example for now. Here is an example with 3 classes. Okay, like I said, I said 3 to 5, just scaled up here, and in the original set, in the original root node, the data, let us say we have 200 data points. 100 of them are in class 2, 40 of them are in class 3, and 60 of them are in class 1, let us say. So for each one of them, you can calculate what is the probability. 60 by 200, 100 by 200, 40 by 200. Okay. So out of this, the maximum probability is for class 2, which is 0.5. Therefore, the impurity index for this original node is 1 minus 0.5, which is 0.5. Okay. Now what we do is, that's right, this is what we have done. Now what we do is, let us say we use some method, something, okay, some variable we use, something, we made a split. We made a split, and we got one region called the left side and one region called the right. Okay, left region, right region. You see in the left region, all the class 2, 100 points, they are still in left region. 10 points of class 1 are in left, and 40, all the 40 from class 3 are still in the left region. Okay, so if you see, totally 150 in class left and totally 50 on the right region. So out of this 150, 10 is class 1, therefore 10 over 150, that is 0.07, is the probability that something will be in class 1 in this region. Something will be in class 2 in this region is 100 over 150, that is 2/3. Something will be in class 3 is 40 over 150, which is 0.27. Out of these, the maximum probability is 0.66. Therefore, impurity is 1 minus 0.66, which is 0.33. Okay. Now, if you look in the right-hand side, all the class 1, class 3 are in the left-hand side, therefore they are 0. 10 in the class 1 is left-hand side, therefore 50 is on the right-hand side. So all the 50 are in class 1, so therefore the probability, maximum probability is 1 for class 1, therefore impurity is 0. Impurity is 0. Now let us do some calculation. Okay, what is the total impurity after the division? Okay, in the left region, 150 points out of 200 have this impurity of 0.33, plus 50 out of these 200 points in the right region have an impurity of 0. Therefore, we multiply 150 over 200 times 0.33 plus 50 over 200 times 0. So the total impurity after the split is 0.25. Total impurity is 0.25. Now you see, originally the impurity was 0.5 before the split. After the split, we got 0.25. The impurity has reduced. Right? Impurity has reduced. Now that gives you an idea. How much has it reduced? How much is it has reduced by original minus nu, which is 0.5 minus 0.25, which is 0.25. So the change in impurity is 0.25. Okay. Now think about this. I could have many splits, many possible splits. Age from 30 to 70, I could have split it anywhere. What will I do? To speed up the process, I will choose that split which maximizes this change in impurity. This change in impurity is called information gain. This delta change in impurity is called information gain. It's called information gain. I want to maximize this. So out of all the possible splits, I will see which gives the maximum information gain, and I will use that as my split. If I have more than one variable, I will do this across all variables and choose that variable with that split which maximizes my information gain. Okay, because see, the impurity has reduced. This is the algorithm we will use to choose the node and the split point. Be it the root node, be it the branch node, doesn't matter. Whatever be the node, to choose that node and the split point, this is the algorithm we will use. This is the algorithm we will use. Same idea you can apply to using what shall I call it? Gini index or entropy. Okay. In some situations, for example, in using classification error, okay, two different schemes can give the same information gain. two different schemes can give the same information gain. And this can be overcome by going to the Gini index. Okay, by going to the Gini index. Okay, so Gini index is given by this. The formula is slightly different from what you saw earlier. Both formula are actually the same. I will leave it to you to prove it. Okay, both formula are actually the same. I leave it to you to prove it. Okay, so Gini index usually exacerbates the difference. Why? While impurity index is 1 minus probability, Gini index is 1 minus probability squared. Right? So if you square a number, okay, even if two numbers are slightly different, 0.45, 0.46, by themselves they might not be very different, but when you square, the difference gets magnified. Right? So Gini index is better in those situations. And of course, entropy is much better. Why? Because it is it's much more than a square. It's actually, as I told you, it's a infinite series. Squared, cubed, power 4, power 5, all these things are added in the log. Okay, so logarithm, so entropy therefore is the one that people by default go to. Okay, but if they have some difficulty for some reason, then people might go to Gini index. Okay, so as a pictorial demonstration, okay, the classification error as the probability for one class increases from 0 to 1, the probability the impurity index is a linear function, reaches 0.5 maximum and then comes down. Okay, whereas the Gini index, which is a quadratic, no, it's like the inverted U here, green dashed line. Entropy actually is this gray line that goes up to 1 on the impurity index, can go up to 1, whereas Gini index and classification error, they only go up to 0.5. Okay, so comparison, we have scaled the entropy also to 0.5, so that will be like this red line. Okay, so the differences are magnified, okay, by entropy the most, Gini index the next, and the least differences in the class difference is caught by the classification error. This is the reason that we go for entropy blindly. Okay. Okay. I'm going to skip this. Now, the question is, I told you, okay, so we solved one problem, namely how to determine the node and what is the split point. Okay, that we do by maximizing the information gain. What is information gain? The impurity index before the split minus impurity index after the split. Okay, and that difference we want to maximize. Okay, that's all. So that way you can identify the node, and it's easy, right? Now the question is, when we have there are two kinds of variables, right? Categorical variables and numerical variables. How do we deal with these two types? Okay, it's a 10-minute session. I'm going to go a little bit longer than usual, but we'll cover this. We'll finish it today. Okay, very easy idea. Let's think about categorical variables to begin with. Okay, so potentially, okay, if you have k categories in a categorical variable, okay, then the complexity can be very high, KC2. What is it? How many ways can you split into binary? See, these are binary decision trees, yes, no, right? That's what we are doing. So we have to split them into two groups. One category in one side, all other categories on the other side. Okay. So now think about this. If you have 20 categories in a variable, then you will have to come up with 20 C2 ways. Is it really the case? Yes. Why? Think about this. Category 1 and all other categories. Category 2, all other categories. Category 3, all other categories. Category 20, all other categories. Okay, that's only 20. Then we can have category 1, category 2, everything else. Category 1, category 3, everything else. So on and so forth. Then category 1 to 3, everything else. Category 1 to 4, everything else. So on and so forth. Right? So this can become extremely complex. Okay. Now, but there is a good thing. This kind of complexity is only when the categorical variable is nominal. What is meant by nominal? Countries. Okay, just categories because there is no relationship. It is not ordinal. It is not integral. Okay, but if it is ordinal scale, okay, it is then much easier. It is much easier. Okay. When it is nominal, there's no other escape. You have to try out these different categories. We split it into, usually we will do split one versus the others. Okay. That's what we usually do. Now, if the category is ordinal is much easier. Why? Because when we split, we have to retain the order. Ordinal means order. That's some ordering. Right? So what is it? Let's say, for example, an example of education as a variable over which we want to split. Okay? Education is one of the variables. So we have this gradation here, right? High school, higher secondary, graduate, postgraduate. Now, there are only few ways you can split this. Why? Because we have to maintain the ordinality of this. We can split, we can pit high school against all the other three, or combine high school or higher secondary and pit them against graduate and postgraduate, or combine high school, higher secondary and graduate and pit them against postgraduate. That's all. Only these three are possible. You cannot do high school, graduate, postgraduate and higher secondary outside. That's not possible because we are mixing the ordinality there. So with the ordinal data, it becomes much easier. And luckily for us, many times we'll have ordinal data. When you have ordinal data, the number of nodes you will have to try out before deciding what is the correct split point is much reduced because we will have to maintain the ordinality. Okay, sorry about that. You have to maintain the ordinality. Okay, how about numerical variable? How do we decide on the numerical variable? This is again, it's actually a very easy idea. It's a very easy idea. Okay, potentially on a numerical variable, there are infinity of split points. Okay, but we don't have to try out all of them. What we do is, if you are going to look at one variable now, sort the data according to that variable. Let's say age. Age is one of the variables in your data. So sort the entire data based upon age. Okay. So start from the lowest age. See what category is that. Come to the next one. See what category is that. If there is a change in category, take the midpoint of these two age values, use that as your split point. If there is no change, continue. You don't have to make a split because they are the same category. Go to the next value. keep repeating this process. But what you do, every time you make a split, find the information gain and choose that split point which has the maximum information gain. For example, in this case, I know I have this variable x. No, initially it's all red. I don't have to split anywhere here. But the moment I go from the second point to the third point, there's a change in class. Therefore, I take the mid value between the second and third point. Okay, I take the mid value. That is the splitting point. And then with that split, calculate the information gain. Keep it. Then next, green, no split, green, no split, green, no split, green, red. Yes, there is a split point. So do a split here. Do a split here. Okay. These two are misaligned. They should come here. Okay. This is this split midpoint between this green and red. Do a split here. See what is the information gain. See what is the information gain. And whichever of these two splits has the higher information gain, use that for your node. Use that for your node. Okay. That is all we are going to do. That's all the algorithm is. Okay, that's all the algorithm is. Yeah, here there is no split. In these two cases, there's a split. Okay, that's all. So numerical variables, dealing with numerical variables is also easy. Okay, it's also easy. Okay, so with these two kinds of ideas, one for the categorical and for the numerical, it is now very easy to find the split points, to decide the nodes. Okay, that is all. That's all. The problem is over. The only problem that's remaining is, where should I stop? Right? Where should I stop? That's the only problem is remaining. That's very easy. It's a very easy one. Why? We can do regularization. We can do regularization. Let's see how we can do that. Okay. So here is some data point. You see, this is really non-linear because everything is in the circle. Everything within the circle is yellow. Outside of the circle is purple. Okay. Linear regression kind of thing will never. Sorry, logistic regression kind of thing will never do a good job. But with decision trees, we could fairly separate the two classes. Right? Fairly separate the two classes. Okay. Oops, what happened? Okay. So here is some. So for this particular decision tree, here is a decision tree plot. Here is the actual decision tree that's shown here. I will leave it as an exercise for you. Just go read through it, but the idea should be clear to you now. How deep should the tree be? That's the final question. That's the only question remaining, right? So here is a tree with depth 4. So 1, 2, 3, 4. We have done 4 cuts here. Okay, 4 nodes. So we got this. If we go to 8 nodes, we got probably much better classification. How far should we keep going? Technically, remember, as I told you, we can build the decision tree very easily till we reach this overfit point, overfit domain, where each subregion is for one data point in the data set is in its own subregion. That's very possible to do. So what we do, like always, we first build the overfit. Right? Regularization, what do? We start with the overfit. Right? We start with the overfit. Okay. And then we increase the value of lambda, go towards underfit, and choose the point where we have the optimal fit. Right? Same thing we do. So here we start with the overfit, and then we start cutting the trees. That's called pruning, cutting the leaves, until we reach a point where we have the optimal classification. Okay, optimal classification. So how do we stop? Decision tree is continuous, no splitting. Okay. So we can keep pruning, okay, until our information loss, in this case, you are going to lose information, right, is within some threshold. Is within some threshold. Or what we can do is, okay, again, something is wrong with my keyboard. I don't know what is happening. Okay. So what we do, cut off the lowest tree, lowest leaves. Okay, you have built everything, lowest level you cut off. See what is accuracy. Then cut off again. See what is accuracy, both for the training and for the test. Keep doing it. So what will happen? Accuracy, okay, when you go from large number of tree nodes, okay, that is overfit. So that you will have a very high accuracy in the training set, right? Literally 100% at some point. But then as you start cutting, the accuracy will keep decreasing until you come to a very small value. So you get to the underfit region. At the same time, when you look at the test data, when you start with the overfit, you have a large error, so small accuracy. But as you start pruning, the accuracy will increase. Accuracy inverse of error, as I told you earlier. Accuracy will increase and reaches a maximum and then start decreasing. So find where the maximum occurs, right? In our case, I do not know what that thing is. Yeah. In our case, the maximum occurs in this region, in this particular example. Okay, the maximum occurs in this region. But you see, but the maximum is a plateau. It is not one point, it's a plateau. So which decision tree should we take? This one, the one with 20 nodes, or the one with 10 nodes? We always go for the simplest model. If you have multiple models that give the same result, then go for the simplest model. Therefore, choose the model with the lowest number of tree nodes, which is this. So what have we done? We looked at accuracy, which is our performance index. We look at the number of tree nodes, which is our complexity index. Put together, we have the regularization. That is what this thing is about. Okay. So this is how we decide when to stop, how deep the tree should be. So you build the full tree and then start pruning it and see how the accuracies vary with the training as well as test set, and find the region where the test accuracy maximizes, and in that region choose that model with the lowest number of nodes. Okay, and that is how we deal with optimizing the decision. Okay, so error rate or accuracy you can have. So if you want to minimize, you have to have error rates. So this will be the inverse of that, plus some regularization parameter times the number of nodes. Okay, so this is what decision tree is all about. As you could see, again, the idea is the same. Okay, I'm not going to continue with cross validation here. Okay, the idea is the same. Okay, you could do as I told you, put the performance, either accuracy or error, and the complexity, which is the number of nodes together. If you use accuracy, maximize this. Usually you go for minimization. So put the error plus tree nodes, number of nodes. So you minimize this cost function. That will give you the optimal tree. Okay. So what is decision tree? Decision tree is a nonlinear classification scheme where we divide the feature space using vertical orthogonal cuts across single variable. Okay, and these are called nodes. The main challenge in decision tree is to figure out what should be the node, and that is done by looking at the information gain. Information gain is calculated using the entropy before the splitting and after the splitting. Okay, that would be the entropy before splitting minus entropy after splitting will be the information gain. That split that maximizes this information gain will act as the node at any level in our decision tree construction. How do we stop? Where do we stop the tree? That's done by doing an overfit and then pruning. This is exactly the same as the regularization scheme we had studied earlier. So draw this regularization plot, that is the errors versus complexity plot, and choose the optimal tree. With this, decision trees are over. Next session, we will meet with some other topic. Okay, probably we'll start with clustering. Yes, John Sirani, please go ahead.
Raja sir, you have one slide where you're talking about stopping the splitting in the graph with accuracy. Is it, I think last before the, yes, not this one, sir. Yeah, this one only. Why this accuracy is coming, sir? This is also one way we can decide to stop splitting. Sorry, I overlooked this. Maybe a few words you can tell.
So what I'm saying is, you do a overfit completely.
Yes.
Go up to the leaf nodes. Everything is a leaf node. Okay, pure leaf node, 100% pure leaf node.
Mhm.
Then what you do is you start pruning. That
Mhm.
is, you are in this region. Okay, let me go here. You have got all these things. Let me do one more thing. Okay. So you've got all these things. Now what you do is you start cutting off at you start cutting off at some level. You cut off at that level. So anything below that you cut off. You see what happens to the accuracy. Then move it to some other level. You see what happens to the accuracy. Move it up, move it up, move it up. Every time you calculate the accuracy. Okay, and keep doing it. So what would happen? Your accuracy initially in the test, in the training set, it will be 100% initially. But then it will slowly start decreasing in the training set. Whereas in the test set, initially the accuracy will be some number, it will not be 100%. But as you start pruning, you are moving away from overfit region. Therefore, on the test data, your accuracy will increase.
Yeah.
And then become a maximum. And then it will start decreasing once again.
Understood. Yeah.
Right? This is exactly like what we saw with regularization, except we saw the ulta of this. Instead of accuracy, we had error. You could do the error in this case. In fact, I am defining the regularization just using errors. Like here, where was this? Here. I'm using error only. So the actual graph will be based upon error, not based on accuracy.
Got it, Rajan sir. Thank you.
Okay, sure. Yeah. I hope, I know I have been a bit fast today, but I think in spite of that, the idea is very simple. It's very easy, very simple. So I think things are clear. If not, of course, you can ask me questions. You can ask me now. You can send it by email. And tomorrow we will start on clustering. And if possible, once we finish clustering, we will start on what is called association rules mining. Okay? So we will finish these two, at least one of them tomorrow, and start on the second one tomorrow if possible. And the one more session that's left for the next Saturday we will finish association rules mining. And if time permits, we will do some more things. Okay. What I want to do is I want to talk about what is called ensemble learning. If time permits, we will do that. If not, what I will do is I will record lectures for the topics that we could not cover in this course. I will upload this in the last session's folder. I'll upload the video for the missing topics, and you'll have something to fall back on when you are learning about, let's say, there is some discussion about ensemble learning, for example, somewhere, and you wanted to know what it was, you could come back and look at those videos. Okay, so I'll try to do some justice there. Okay, with this, I'll stop here. If you have any questions, we can continue. If not, I'll see you next week. Okay, and not next week, tomorrow. I'll see you tomorrow, Sunday. Thank you all. Take care. Have a happy Sunday.
Thank you.